entire B of this year. Okay. Now, almost all we have finished the first 9 units. Now this is the last class, and B of we have explained. We must explain here some other important theorems and inequalities operators. Okay. Only total out of 18 units, 9 units successfully completed. And one of the important session, this is inner product spaces and inequalities. Okay. And operators. Okay. Now, first of all, you have to see the screen share. Okay, students. Now, this is one of the most important concept in functional analysis and the total analyzation of this part. Already we have learned in undergraduation level, that is vector algebra or linear algebra. So, you have to practice the inner product space. What is the inner product space? And first of all, we must know the definition of inner product space, and throughout the linear space definition, and we must explain the definition of inner product space. Simply, that is IPS, inner product space, for short form as IPS, means inner product space. What is the definition of inner product space? First of all, we must assume here one of the non-empty set. That is this is a 10th unit, students. Listen carefully. You must verify previous papers, and without this concept, we can't expect anyone here. Okay, especially this is inner product space part. Define inner product space and Euclidean space, unitary space, and state and prove Cauchy-Squarge inequality. These are all important questions. These are all important concepts, especially in this unit. Okay, define inner product space and Euclidean space and unitary space. Prove, state and prove Cauchy-Squarge inequality. And second one, triangle inequality. Third one is parallelogram law. Okay. Now these are all very important concept, especially in this unit. First of all, what is the inner product space definition? First of all, we must assume here capital X be any one of the vector space. Given this vector space, over the field of the field here that is denoted by here, the field of the part is K. Okay. Those field of the elements are scalars. Here, those field of the elements are either real numbers or complex numbers. So we must assume here capital X under inner product is denoted by this is. Okay. Now this is the function of inner product. Function on vector space of function of the inner product on vector space is, that is the notion. Under less than and greater than, we must denote the dot product is there. So this is the product of the part lies between the less than and greater than. So it read as inner product on vector space or linear space. So that inner product is defined from X cross X to capital K. K means that is the field of the elements are scalars, such that under the following axioms are satisfied. Define inner product space means let inner product of a function on vector space is defined from X cross X to capital X. Here, field of the elements are either real numbers or complex numbers. Is said to be an inner product space. Hence, the following conditions are satisfied. Here, first one, non-negativity condition. We must assume that any one of the vector is here X be any one of the vector space. Here X be any one of the vector in vector space or linear space. Now that vector is the non-negativity condition is applicable here. So x and x, inner product of x and x is greater than or equal to 0. This condition is called positivity condition. Positiveness means that is the non-negativity condition is there. If and only if, suppose here x and x, suppose according to this inequality, positiveness means greater than or equal to 0. Suppose if it is x equal to inner product of x and x equal to 0. So if and only if x equal to 0. So this is called a null or zero vector on zero vector of capital X. So inner product space, before the definition of inner product space, that is the first condition throughout the function. Here inner product of x and x is greater than or equal to 0. So that is called positiveness or non-negativity condition. Second one, linearity is applicable. So we must assume here x, y, and z. These three are vectors in vector space or linear space. Okay. Suppose here in between any two vectors, addition of any two vectors, that is x plus y with respect to z. Inner product x plus y with respect to z. How to distribute this one? So inner product of x and z plus inner product of y and z. Now this is called a linearity property. And at the same time, scalar multiplication is also applicable here. What is the scalar multiplication? Alpha x. So here x and y be any two vectors in the vector, that is the vector space. Now here the scalar multiplication with respect to y. So alpha be any one of the field element. So we are taking the outside of this part, alpha of inner product of x and y. That can also be written as alpha of inner product. It read as inner product x and y. Okay, now this is the linearity condition. And IP3, it read as conjugativity. Conjugate of inner product x and y equals to inner product y and x. Now this is the conjugate of x and y equals to, now that is the inner product of y and x. Suppose conjugate of alpha and beta. Now that can also be written as beta and alpha, inner product of beta and alpha. For here x and y, there are two vectors in the vector space. Okay. Now this is called, a bar notates, denotes the conjugate in K. K means that is the over the field of the real numbers or complex numbers. Now it read as conjugate of inner product x and y equals to inner product y and x. Now when these three conditions are satisfied, so that is the third one is called conjugate symmetry. So IP means inner product third condition, inner product second condition, inner product first condition is positive definiteness. IP1 is called positive definiteness. Please see and verify this one. Your textbooks also. Okay. According to the screen share, now that is the IP1 means positive definiteness, and IP2, inner product second property, is called linearity of the inner product. Okay. Now third one, IP3, is called conjugate symmetry. Okay. Now IP3 is called conjugate symmetry. When these three conditions, these three conditions are satisfied, that is called an inner product space. Suppose field of the elements are real numbers. Already from the beginning of this class, from the beginning of the functional analysis or overall analyzation part, field of the elements, when the field of the elements are real numbers, that is called real vector space. Now, especially in this one, inner product space, when the field of the real numbers is called real inner product space, that is RIPS. Suppose field of the elements are complex numbers, that is called complex inner product space through the IP3 condition. Okay. Suppose at the same time, real inner product. Hello? Any doubt? Okay. Suppose here, real inner product space is also called Euclidean space. Suppose the K equal to C, field of the elements are complex numbers, that is called complex inner product space. Now, according to this one, IP3 condition means conjugate. Students, listen carefully. This is the mistake. Bar notation is here. Conjugate symmetry of x and y equals to y and x. Okay. Here, suppose without conjugativeness, because here field of the elements are real numbers. So this is conjugative is not necessary here. X and y equals to y and x. See here, inner product of x and y is also consisting real set of real numbers. Okay, this is called conjugate of a real numbers. This property is called here x and y equals to inner product of y and x. This is called conjugate of real numbers because there is no bar notation. Suppose bar notation is here. So that is it read as conjugate of x and y. Here the field of the elements are complex numbers. So that is inner product of y and x. That is called conjugate of complex numbers. Okay, students. Now, the above definition, how to deviate the linearity property and in the second way or another way. Now, x distributes with respect to y and z. So this is y plus z is the addition of vectors. Now, first coordinate part is x be any one of the vector, x distributes of y and z in between the vector addition. So it read as x and y plus x and z. Now in the same manner, can also be written as conjugate symmetry property. Now it can also be written as conjugate of y plus z and x. Okay, that is the by IP3. Now it that can also be written as y and x, conjugate of y and x plus z and x. Now at the same time, conjugate of individual of the part of, this is enter the part of y1 plus y2, suppose. So conjugate y1 plus conjugate to y2. Now that is the conjugate is also distributed under a vector addition. Now this value is conjugate symmetry property IP3. So this value is x and y. Now this value is inner product x and z. So finally, with respect to scalar multiplication, so x of alpha and y. So conjugate of alpha y and x. Now conjugate of alpha of yx. Now this is a conjugate of alpha and conjugate of y and x. Conjugate of y and x is x and y. So x and alpha y can also be written as according to the conjugate symmetry property, conjugate of alpha, because alpha be any one of the real number. So that is not necessary here. Alpha bar is nothing but alpha. Now here alpha bar equals of inner product of x and y. Now this is the there are two simple IP3 conditions. Now this is also one of the short answer question is given by the conjugate symmetry. X of what is the value of x and of x of y plus z and x of alpha y. That is the inner. It read as x of alpha y means inner product of x of alpha y. It read as inner product of x of y plus z. Okay. So again, this is the definition of throughout the complex numbers is also well defined. Okay. Throughout the complex numbers is also in the same manner. Now the above the definition throughout the real numbers, either real numbers or complex numbers. Now that is the definition of inner product space. See the examples of inner product space. Okay. Now here X be the set of all. This is the physical interpretation for inner product space. Let X be the set of all forces in the space acting at a point 0. Now this is the 0 means that here we know that each force has magnitude and direction. Every force must have magnitude and direction. So length of the simply magnitude and direction means suppose you are taking in any two vectors. Okay, so that is x and y or alpha and beta. So any two vectors are equal. How to calculate the equal of vectors? Same length, same direction, same magnitude, same sense. Okay, same support. Now, any two vectors are equal means, especially in the space region, all the space of the inner elements are called vectors. Outside of the elements are called field of the elements, that is called scalars. Students, listen carefully. Now, enter the, just you have to imagine the physical interpretation means this is the space, enter this concept is applicable in ISRO. Okay. Enter the space part is also applicable. Enter this concept. Because here, suppose we are taking the x be the set of all forces. Okay, set of all forces in space acting at a point origin means a 0 at point 0. Now every force, each and every force must has magnitude and direction. So that is denoted by x, the direction of x, direction of y, direction of z. Now it read as x, that is the x vector, y vector, z vector. So this is the length of the part. This is the direction, x direction, y direction, z direction. Now these are all elements of set of all forces in the space region. The force whose magnitude in 0 will be denoted by 0 bar. 0 direction means null direction. So this is the 0 element of capital X. Now, what is the resultant of the force of X and Y? Now, that is the definition of X, addition in between the X direction and Y direction means X bar plus Y bar. Multiplication of the part is X into Y. Throughout the multiplication, scalar multiplication, lambda is also be any one of the scalar. We are applying with the X bar vector. So that is scalar multiplication is lambda X bar. So that is the here lambda of the magnitude is it is denoted by magnitude is denoted by mod lambda. So suppose suppose it is in the same or opposite direction of X according as lambda is greater than 0. Either that scalar lambda greater than 0 or less than 0. Suppose lambda X equal to 0 here then automatically if lambda equal to 0. Okay. Now this is one of the example. So inner product on X, usually this is a dot product. This product is called inner product of the point is called, this is the dot product of vectors representing the forces. So that inner product is denoted by dot product. If here X and Y belongs to capital X, define inner product space, give examples means this is the first example. So inner product of X and Y equals to, it can also be written as the force of the direction. So that is X plus Y. Simple force, when the force is applicable, X bar, mod X bar and mod Y bar. This is the also, it read as mod means absolute of X bar and absolute of direction of Y or Y bar is there. Now this is the cos theta because angle of the representation in between the forces cos theta is there because that is the adjacent by hypotenuse. Okay. So now in between the value is angle between any two vectors formula. This is also X and Y is also represented as XY cos theta. Now when the inner product is applicable, inner product of X and Y equals to, so that is a mod X and mod Y of cos theta is there. Here X represents the magnitude of the force X bar and theta is the angle between the lines of action of forces X bar and Y bar. Okay. Now according to this one, so that inner product is an inner product on X. It is a real inner product space. So one of the example is X under inner product is a real inner product space through this one. The set of all forces in space acting at a point 0. So here according to this one, okay, students, listen carefully. Now first condition is positive. So this is one of the example is X under inner product is a real inner product space. At the same time, this is also called field of the real numbers is called real numbers. So that is the real inner product space or Euclidean inner product space. So suppose field of the elements are complex numbers, that is X under inner product is a complex inner product space. So that is also called unitary space. First one is the positive definiteness condition of IP. So X and X equal to, through this definition, X and X equals to mod X and replacing Y by X is there. Mod X and mod X cos theta. So enter that value is greater than or equal to 0. Simply enter this concept is if and only if suppose X bar equal to 0. Say, this property throughout this one. This is called when the X given the vector, given the magnitude of the part is 0. So that is called a null or 0 force of X. So force, this is the physical interpretation of on inner product space. Second one is the linearity. So it can also be written as X and Z plus Y and Z of cos theta. Okay. Simply that is X and Z plus Y and Z. Here the cos theta is the when the unit vector, unit part for all here X and Y, Z is also these three elements are also forces of the magnitude of the vectors. Third one, conjugate symmetry. When these three conditions are satisfied in the physical interpretation, so that is X and Y equals to mod X and mod Y of cos theta. Again, enter the concept can also be written as this is the conjugate to, third one is the conjugate symmetry. So this is a conjugate is applicable. So mod Y and mod X cos theta. So conjugate of Y and X can also be written as. So this is the real inner product. That's why here inner product of X and Y equals to inner product of Y and X. So, okay, that is the, here the bar denotes the, now this is the bar notation. Okay, bar is also, this is the meaning of enter the bar of inner product of y and x. So bar denotes the conjugate of the conjugate in the field. Now this is the second example, n tuple of the real numbers. We are taking n tuple of the real numbers is also an inner product space throughout the vector addition and under scalar multiplication. This is the one of the finest example. Okay, finest means finest example. Okay, simply. So we are taking alpha and beta. There are two vectors given in this n tuples of the part. Here, n tuples of the real numbers. So that is called n consisting of the elements are alpha 1 up so on, alpha n, and beta the vector. You are taking the beta 1 so on, beta n. So under the vector addition is also applicable alpha 1 plus beta 1. That is the first coordinate vector. Second coordinate vector beta 1 alpha 2 plus beta 2. And nth coordinate vector alpha n plus beta n. So scalar multiplication lambda of alpha. Here alpha means alpha 1 so on alpha n. Now that is lambda alpha 1, lambda alpha 2 so on, lambda alpha n is there. Here n tuple of the real elements alpha and beta values is also belongs to capital X. Here lambda being any one of the real number. Okay. Now according to this one, we must prove that given this n tuples of the real numbers, is it an inner product space or not? So according to the definition of IPS, first of all, positiveness, inner product of alpha and beta. Now that can also be written as a summation of I varies from 1 to n, because it is consisting of n tuple of the elements, n tuple of the elements. So alpha I values means alpha 1 so on alpha n. So that can also be written as alpha I and beta I. So here inner product of alpha beta, here the defined part summation I equal to 1 to n alpha I beta I. So this is the from the given this example throughout the definition of this part. Okay, here the inner product is an inner product on capital X is there. Suppose we are taking one of the vector is here alpha being one of the vector. So that vector is can deviates the alpha 1 so on alpha n. So this vector is also consisting given in this part vector space or linear space. At the same time, replacing because same vector is also in the first positiveness part, alpha and alpha can also be written as summation alpha I square. Here I varies from 1 to n. Okay. Now when the this according to this condition positive definiteness, here alpha and alpha is greater than or equal to 0. So that is the first property of inner product. Okay, when the suppose if alpha and alpha, the inner product of the alpha and alpha equal to 0, then automatically alpha I values are 0. Alpha I value 0 means alpha 1 equal to 0, alpha 2 equal to 0 through this definition of summation alpha I square. So that is also 0. So each and every element of given the vector of alpha, so each and every one is 0. So this is also called a 0 vector of n tuples of the real numbers. This is the first condition verified. And in the same manner, second condition, that is the linearity part. What is the linearity? Here alpha, beta, gamma are any three vectors in R power n, means that is the n tuple of the real numbers. So here gamma distributes. This is gamma, not R. Students, this is the gamma. So now you have to understanding purpose. We are taking the R is also, there is no problem, because according to this the unknown symbols are, we are taking the unknown symbols. So those are all vectors. Here in between the vector under vector addition, alpha plus beta with respect to gamma means summation of alpha I plus beta I of gamma I. Now it can also be written as summation alpha I and gamma I plus summation of beta I and gamma I. Okay. Now that is the, now it can also be written as by the definition of in the above part, here alpha and beta. Okay. This is inner product of alpha and gamma. This is of inner product of beta and gamma from the above first condition, first equation. This is the first equation. Okay. Now, say another one, scalar multiplication. Here lambda of alpha and beta, lambda alpha I, beta I, that is the summation of this part. So we are taking the scalar of the part, taking outside. So lambda of that can also be written as lambda of summation alpha and beta I. So lambda of this is inner product. By the definition of first equation, it can also be written as lambda inner product of alpha and beta. So this is the linearity condition is also verified. Third condition is what is the third condition of inner product space? Students, please respond. What is the third condition? Anybody is here? Hello? Third, what is the third condition? Conjugate symmetry. Okay. So
Yes,
inner,
sir.
yes, the inner product of alpha and beta can also from the first equation summation alpha and beta I. Now this is the by commutative property that can also be written as beta I and alpha I. Because here alpha and beta both are n-tuples of the real numbers. That's why conjugate is not indicates that is not necessary here. So if it is the complex numbers, now you particularly you must mention the conjugate of this part. Because here alpha and beta both are field of the elements are real numbers. So enter this part can also be written as summation of inner product of beta and alpha. So conjugative property is also conjugate symmetry is also verified. So second example, n tuples of the real numbers is also an inner product space. Okay, in the same manner, n tuples of the complex numbers, that is also an inner product space. When these three conditions are verified, that is the simple part. Particularly, a second vector is here alpha and beta. See this one. By the definition of given the field of the elements are complex numbers, so here alpha and beta inner product can also be written as summation alpha I and second vector particularly denoted by beta I bar. This is the conjugate of this part. Okay. Bar denotes the, now it read as conjugate of the part because that is the particularly given the field of the elements are given the vector space of the elements are n tuples of the complex numbers. That's why denote the second vector is also particularly denote the bar indicates of the bar. So that it simply read as conjugative symmetry. Okay. Now here x equal to n tuples of the complex numbers under inner product is also a complex inner product space. This is called unitary space. Students, listen carefully. Field of the elements are complex from the beginning of online classes, starting of and before the introduction of functional analysis, overall the field of the real numbers is called real space or simply that is Euclidean space. Okay. Field of the elements are complex numbers, that is called complex space or complex inner product space. Don't deviate, especially this part. Please stay on the line. Please stay on the line, students. Okay. Now here x equal to n tuples of the complex numbers under inner product is a complex inner product space. Now here the third one, L2. What is the meaning of L2? Now, for all the this is the third unit of this part, LP spaces means that is the linearity elements given the consider the set capital X equal to L2 of all complex sequences. Okay. Now, suppose one of the sequence say alpha equals to sequence of alpha n, beta equals to sequence of beta n. So these are all complex numbers such that the series summation mod alpha square is convergent. Okay. Complex numbers such that the series summation mod alpha square is convergent. Now, it is defined on capital X defined here alpha equal to sequence of alpha n, beta equal to sequence of beta n. There are two elements given in the L2 part. L2 part is here capital X. So that is L2 means. Okay. Okay. Here lambda be any one of the complex number. So how to define the alpha and beta? Through the sequence of alpha n plus beta n. Lambda alpha means lambda alpha n sequence. So through the sequential part, here the defined inner product of alpha and beta means summation alpha n plus beta n because the definition of AB to AB. Now these terms are involved in a plus b whole square. So enter the concept a square plus b square plus 2ab or a square plus 2ab plus b square. Okay, enter the concept because the product of AB is when the AB is 0, Now enter that value cannot exceeds the a square plus b square. So absolute of alpha n plus beta n whole square equals to that is it cannot exceeds the mod alpha n plus mod beta n whole square. So through the algebraic law or property of arithmetic that is the property of algebraic laws. Okay. Now a plus b whole square, that indicates the a plus b whole square. It can also be written as mod alpha n square plus 2 alpha n, 2 mod alpha n, mod beta n plus mod beta n square. So this value is also, that is not considered here. Now here the beta n can also be entered. This concept can also be written as mod alpha n square plus mod beta n square, because these values are 0 is there. Okay. Now summation mod alpha n plus beta n whole square cannot exceeds the 2 of summation mod alpha n square plus 2 mod beta n square, because this is the 2 mod alpha n square, this is the 2 mod beta n square. So this is also it indicates the parallelogram concept. Okay. So enter the concept, enter this value is less than infinite. Why? Because these are all L2 spaces, means that is the complex of this part. Enter the alpha equal to mod alpha n, beta equal to mod beta n. So alpha plus beta is also belongs to x. So finally, enter the throughout the vector addition and multiplication of complex numbers. Okay, just already you have to discuss here. Enter this value is less than infinity, means L2 or LP spaces, means enter the linearity, 2-dimensional of the linearity, 3-dimensional of the linearity, and nth dimension, pth dimension, because the p lies between 1 to infinity. That theorem is also there. That is the 5th unit. So enter LP spaces part must be repeated. This part is also measured integration and operator theory paper. So that papers are 9th A and 11th paper. Okay. So this is one of the finest example of inner product through and L2 space. L2 and inner product is also an inner product space. Okay. Now, is it absolutely convergent? Already we know the property of absolutely convergent series is convergent. And according to this condition, Cauchy's quad inequality, here summation alpha n and beta n is also a convergent series. Okay. So here alpha n converges to alpha, beta n converges to beta, such that in this way, mod alpha n and beta n bar is also converges to mod alpha beta bar. Okay. So through the Cauchy's quad inequality, already we have learned in undergraduation level. Students, listen carefully. Now, this is very much more interested content, especially in this analyzation of part. Summation mod alpha n and beta n bar equal to summation mod alpha n bar and mod beta n. So that can also be written as summation alpha I square and whole power 1 by 2, summation mod beta n square whole power 1 by 2. Enter that value is less than infinite. So this concept is summation alpha n and beta n bar is absolutely convergent. That's why that is also convergent. So when according to this property, here the second one, this is the positive condition verified. Here alpha and alpha can also be written as summation mod alpha n whole square. Similarly, inner product of alpha and alpha equal to 0. Again, alpha n equal to 0 according to this. This is the 0 vector. And the linearity condition is also verified. Alpha plus beta with respect to gamma. And lambda alpha with respect to beta. So that is lambda of inner product of alpha beta. And conjugate of alpha and beta, because conjugate is also applicable here. Why? Because given the elements are complex numbers. That's why conjugate is also indicates alpha and beta in between the inner product. So that's can also be written as inner product of what is the value of this one? Beta and alpha. Now through this one, alpha, this value is summation alpha n and beta n bar. And again, this value is summation conjugate of alpha n and beta n bar. So this is summation alpha n bar and conjugate of conjugate beta n. Conjugate of conjugate is simply that is beta n. So this value is an equivalent to conjugate, that is inner product of beta and alpha. So x equal to L2. This is the direct example. How to write the example? Given the inner product space, when given the inner vector space, When it is L2, it is also an inner product space over the complex field with respect to the inner product. Okay. This is the third example. Fourth example is complex valued functions defined on closed interval 0, 1. This is also given the set. Now, this is the simple mentioned, not verified here. Okay. Just define. Now, this type of question is given in the final examination. Students, listen carefully. Now, here capital X equals to script C of closed interval 0, 1. Now, this is, it read as the set of all complex valued functions defined on closed interval 0, 1. Okay. Now, this is also an inner product space under the vector space, under the inner product. Here, the space of the elements when it is the complex valued functions on closed interval 0, 1. Now, that is also when these three conditions are verified. Suppose we are taking the f, g be any two complex valued functions, lambda be any one of the complex number, that is the field of the element. So that is the f and f greater than or equal to 0 through this definition. F plus g of t equal to f of t plus g of t under the vector addition in between the complex valued functions, and lambda f of t. This is the scalar multiplication under the vector space condition. So lambda into f of t. So these, according to these two conditions, here the defined part, inner product of f and g, defined part is integral, because this is the closed interval 0, 1 means now this one, it referred as integral 0 to, now this is the meaning of integral 0 to 1, f of t, and the second function is conjugate g of t dt. So through the, this is the continuous of complex valued functions defined on closed interval 0, 1 means that is the integral 0 to 1. So that is the in between that you are taking any two functions f and g, integral 0 to 1 f of t into g bar conjugate of g of t and dt. So through the integration on the Riemann sense. So this is the Riemann integrable concept. So integration sense on Riemann integral part. So under the functions of f and g on inner product equals to, that is the defined part is there. According to this condition, these in the IP1, IP2, IP3, these three conditions are verified. F and f is greater than or equal to 0, then automatically f equal to 0. So that is the meaning of mod f of t whole square is greater than or equal to 0. F of t into conjugate of f of t dt means that is mod f of t. Already we have to learn in the primary part of complex analysis. Okay. Complex analysis mod z means z into z. Simply that is mod z square means z of z is there. Z and z bar. So that can also be written as z into z bar means mod z square. So here z replacing z by f of t is there. So f of t into f of t bar by the definition. So mod f of t whole square dt is greater than or equal to 0. So entire the concept is greater than or equal to 0 for all t lies between the, okay, t lies between the, what is the, t is also consisting of closed interval 0, 1. Okay. So the second condition, we are taking three functions f plus g with respect to h. So integral 0 to 1, replacing f by f plus g of h of t bar. So this is f of t and h of t plus g of t and h of t. So this is the definition of f and h. This is the definition of inner product g and h. Okay, through the integral concept. Now, how to take the integral concept? Now, and given the function of the variable is also consisting of a set of all continuous functions defined on closed interval 0, 1. So enter all the intervals depends upon the integral concept. Okay. So scalar multiplication lambda f of g. So this is lambda of f and g. So integral 0 to lambda of integral 0 to 1 f of t and mod g of t. Because this is the complex valued functions, that why second function we are taking the conjugate. So this is the definition of inner product f and g is there. So third condition, conjugate to symmetry is also verified. Conjugate of f plus g. Conjugate, not plus is there. Students, please This is the mistake. This is conjugate of f comma g, not plus. Students, please rectify this mistake. This is the conjugate of f comma g. Are you okay? Please.
Okay, sir.
This is comma. So conjugate of inner product f comma g equals to integral 0 to 1 conjugate of f of t and g bar of t dt. So this is, it can also be written as integral of simply integral is means that is closed interval 0 comma 1. This is the definite integration f of t bar, and conjugate of conjugate means simply that is g of t. So by the definition, this value is inner product of g and f. So third part is also third in IP is also verified. So given the vector space set of all complex valued functions defined on closed interval 0 comma 1, this is also called complex inner product space. So some examples are real inner product space, and some other also we have to verify some another examples of complex valued functions. So this is the complex inner product space. Particularly in the examination, listen carefully. Define inner product space. Give any suitable example of a real and complex inner product space. At least one is there. So you must mention the one real inner product space and one complex inner product space. This is one of the most important. So understand according to the subject, according to this concept, then easily to mention that answer. Okay. So this is one of the complex inner product space. One of the example. In the same manner, so Lebesgue, some students are also referred as Lebesgue. Okay, not Lebesgue. Okay. Now this is Lebesgue. Yes, silent. Now it read as Lebesgue measurable sets in open interval AB. So consider the interval AB of the real line is there. So on the real line, open interval means A less than X less than B. Okay, closed interval means this is the square bracket. Okay, closed interval means closed interval A less than or equal to. Closed interval means A less than or equal to X less than or equal to B. So here X be any one of the element. That element is lies between any two real numbers. So that's why it read as open interval AB. So this is one of the real line. So recall of the definition of Lebesgue measurable sets in open interval AB. So Lebesgue measurable sets is also an inner product space. Throughout the integration, here F being the collection of measurable functions. The collection of measurable functions on Lebesgue integrability, a real value defined on open interval AB. So F be any one of the Lebesgue measurable function of the L2 of AB means the Lebesgue measurable on AB is there. So that is the definition of integral A to B mod f of t whole square dt. So that value less than infinite. Okay. Now this is the Lebesgue sense. Okay. Lebesgue measure and integration. Now we know the following the facts are there. Now enter the concept. Lebesgue concept is also much more important in measure and integration. That is the paper number 90A. So Lebesgue monotonic convergence theorem, Lebesgue dominated convergence theorem. Okay, students. Now these theorems are very important concept in the ninth paper A. Ninth A means that is the M and I. So M and I means measure and integration paper. So particularly these theorems are very important in measure and integration. Okay, and without my concept of, because that is not my session. Of course, enter the my mathematical papers. I must explain each and every paper important is there. Okay, so measure and integration is also one of the analyzation paper. So that's why I am telling here one of the important theorem in measure and integration. State and prove. First theorem is the Borel sets. Okay, Borel is also one of the mathematicians. Borel sets is also Lebesgue measurable, one of the important theorem. In the same manner, so Lebesgue monotonic convergence theorem, Fatou lemma, Lebesgue dominated convergence theorem, monotonic convergence theorem, and at the same time, okay, please stay on the line. Now these theorems are very important in M&I paper. Okay, and Agrove theorem, EGO ROVE, apostrophe Agrove theorem. Okay, these theorems are very important, especially very important in M&I paper. So according to the Lebesgue measure, these properties are very important. Sum of any two measurable functions and the multiplication of measurable functions is also a measurable function. That is one of the property. Now this property is also in M&I paper, that is 9th A paper. So now here A and E means almost everywhere. What is the meaning of AE? A dot E means this is the almost everywhere. So any two measurable functions are said to be equal almost everywhere, means F equal to G. This theorem is also very important in M&I paper. No, that is the introduction of the concept of functional analysis. That's why I have explained here. Okay, here T is F means simply that is F of T. So T means T is also consisting of open interval AB. Okay, so Lebesgue measurable sets of Lebesgue measure 0. Lebesgue measurable set of Lebesgue measure 0. Now throughout this roster form, here F equal to G almost everywhere. This theorem, second property is also very important. Okay, and these properties are F measurable and absolute function is also measurable. This theorem is also very important. So here F and G, the any two measurable functions, F less than or equal to G almost everywhere, and throughout this Riemann condition, throughout the Riemann condition. So integral A to B F of T dt less than or equal to integral A to B G of T dt. So consequently, F equal to G almost everywhere. So both integrals are equal. Suppose if F is a non-negative measurable function on open interval AB, here F equal to 0 almost everywhere. So this condition, these 5 properties belongs to measure and integration paper. Don't mislead here. Okay, try to understand my concept. Okay. Now these are all very important concept of Lebesgue measurable functions. Lebesgue measurable functions is also now when these three conditions are verified throughout the integrable part. This is the integrable part. Integral of F, integral of G, integral of H. There are 3 arbitrary members of L2 of AB. So integrable concept. Okay, integral part is also an inner product space on Lebesgue measurable. So this is also one of the finest examples. Students, listen carefully. Okay, and just you have to verify these are all well-defined examples of inner product space. Sometimes this is also given, that is not necessary here. Students, one of the important theorem, Cauchy-Squarge inequality. Please note down, very, very, very important in the final examination. And through the definition of inner product space and examples, and give the question. This type of question is given how to define, how to give the question. State and prove Cauchy-Squarge Bunkowski inequality. Now it read as a Bunkowski inequality. Bunyakowski, not Bunyakowski, Bunkowski inequality it read as. Simply that is Cauchy-Squarge inequality. Okay. Now this is the 10.5.1. What is the statement? Please, anybody is here? Please state the statement. Please study. Please tell me the statement. Let X under inner product be an inner product space. We are taking in any two vectors. Here X and Y be given the inner product space. Absolute of inner product X and Y whole square less than or equal to inner product of X and X, inner product of Y and Y. Students, that is the simple statement of Cauchy-Squarge inequality. Okay, please stay on the line. Please stay on the line. Students, once I have to repeat here, once I am telling up to 6:15. Please observe the time. Up to 6:15. Enter the concept of functional analysis according to the subject. And the last 15 minutes, I will give some important questions in further units. Okay? Please respond.
Okay, sir.
Okay. Now, Chandni, you must respond here. Only one of the students respond, and some other than is also not respond here. Okay. Sudhari Srilil. Now this is the last session. Please respond here.
Yeah, yes, sir. I'm here.
Students, if you have any doubts here,
Yeah. No, sir.
okay. Metro E of T power. So the okay. Chandni okay. GK. Sir, student GK sir. GK is also Sutari Srilekha. Please stay on the line. I will take the attendance. Okay. Okay, students, up to 6:15. Now, enter the concept is also here, defined here. According to the subject, I must explain up to at 6:15 p.m. Last 15 minutes, I will give the further units of some important questions. Okay. Now, this is the statement of inner product, Cauchy-Squarge inequality. Here, X and inner product be an inner product space. Here, X and Y belongs to capital X. Absolute of X and Y whole square less than or equal to inner product of, now that can also be written as inner product of X and X and inner product of Y and Y. Okay. Now, that is the statement of inner product space. Now, how to define the proof? First of all, second vector, suppose we are taking the either any vector is 0, either X or Y, suppose any 0 vector is 0. So, enter the inner product of XY equal to 0 or inner product of X and X equal to 0. Now, this is X. Students, please rectify this mistake. This is X, not Y. Are you rectify here? This is X, not Y. Please observe this mistake. So, if any vector is 0, either x0 or y0, so x and x0 or y and y0. So, that is the RHS part. Okay. Suppose any vector is 0, so both inner products are 0 is there. So, by the above inequality holds good. Now, that is then automatically theorem holds good. Statement is already well defined. If any 0 vector is there, we are taking in any 0 vector, then automatically defined in either LHS or RHS, either left hand side or right hand side. So, both are 0 is there. Okay. So, in the above, first of all, case 1 is also verified. Suppose either y not equal to 0. That is the second case. Our assumption is y non-zero or another arbitrary scalar is any scalar is, we are taking the any scalar, lambda is be one of the scalar is there. Okay. So, first condition is non-negativity, positive definiteness. Positive condition, positive definiteness of inner product space definition. So, that's why we are taking the x plus lambda y. We are replacing y by lambda y is there. So, here replacing x by x plus lambda y, y by x plus lambda y. So, enter the concept inner product of x plus lambda y, where y be non-zero element is there. So, that's why scalar multiplication is lambda, because through the scalar lambda y is taken. So, in between the x and lambda y under vector addition is also submitted here. So, inner product of x plus lambda y and x plus lambda y is also positive definiteness. So, that is the non-negativity. So, how to define this x plus lambda y and x plus lambda y in between the inner product part is there. So, this is the x and lambda y plus lambda y and x plus lambda y and lambda y. Now, this is very simple and interesting concept. Now, this can also be written as inner product of x and x. Now, lambda, this is the second coordinate of second part. So, in this region, lambda be the along with the y. So, this is the second coordinate vector in this ordered pair. So, lambda bar, taking outside lambda bar of inner product of x and y. This is the first, this is one of the ordered pair, lambda y and dx, lambda y and dx. So, lambda is the real, this is the real. But here, this is the second ordered pair of second coordinate vector. This is the complex element. That's why we are taking this is lambda bar. This is the complex field of the element. This is the real element, first ordinate vector. So, lambda of y and x. Now, this is lambda into lambda bar. This can also be written as lambda into lambda bar of y and y. Now, finally, x and x, lambda bar of x and y Now this can also be written as lambda of this is the conjugate symmetry. According to the conjugate symmetry, it can also be written as the inner product of conjugate of inner product of x and y. Plus this is lambda into lambda bar. This is the complex analysis. Lambda into lambda bar means simply that is mod lambda square of y and y. So y not equal to 0 and inner product of y and y is also greater than 0. So that's why lambda equal to, enter this value is lambda equal to inner product of x and y by y and y. We get from above the concept, we are replacing the value because y be the non-zero. So inner product of y and y is greater than 0. We are taking the value is, what is the value? Taking the value lambda equal to inner product of x and y and y and y. X and y by y and y. So replacing this value in the above expression. Okay. So according to this one, this value is, what is this? Equal to, this is the value of equal to inner product of x and x minus, now this is a conjugate of x and y and x and y. So that is the meaning of z into z bar means mod z square. Here z equals to inner product of x and y. So z into z bar means mod z square, replacing z by x and y. Okay, minus this is also mod x and y whole square. Okay, plus this value is also same. Okay, finally we are getting the value is what is that? So these two values are cancelled here. Finally, we are getting the values mod x and y whole square by y and y is less than or equal to x and x. Only there are two values is given. Enter this value is greater than or equal to 0 because these two are cancelled. Okay. Finally, inner product of x and x minus mod x and y whole square by mod y and y is greater than or equal to 0. So this value is shifting into this side. So finally, mod x and y whole square by y and y, now on the reversal part, less than or equal to x and x. Okay. So finally, when the cross multiplication is here, mod x and y whole square is less than or equal to so that is our problem. Okay. Mod x and y whole square less than or equal to x and x and y and y. So that is the proof of Cauchy square inequality. Students, listen carefully, especially students. Can you hear me? Now this is the proof of Cauchy square inequality is here. So by the above condition, inner product of x and x is less than or equal to 0. X and x is less than or equal to 0. For all here, x be any one of the inner product space element. Now, how to define the norm? Norm x can also be written as the positive value of square root of inner product x and x through the Cauchy square inequality. Now, this value is also applicable in the Cauchy square inequality. So, that is mod x and y whole square less than or equal to, this is the value of norm x. Square root is also applicable this side. Square root of x and x and y and y. So simply stated as mod of inner product x and y less than or equal to norm x and norm y. So square is also converting into this side. Square root is also taking, we are taking the square root on both sides. So square and root is also cancelled. Finally, we are getting the mod inner product of x and y by the definition of a norm. So that value is, this is norm x and this is norm y because square root is applicable. Square root of x and x means norm x. Square root of y and y means norm y. So this is also Cauchy square inequality. In sometimes Cauchy square inequality is stated as inner product of x and y less than or equal to under the norm condition. So that value cannot exceed the norm x and norm y. Okay. Now this is the Cauchy square inequality. Students, listen carefully. So we are taking the more generally. Suppose here x and inner product means this is the x and inner product. It is also reduced in the inner product. Okay. So this statement can also be referred as here we are taking the elements are linearly dependent. When the linearly dependent means replacing x equal to alpha y. So replacing because given the linearly independent, how to justify the linearly independent in Cauchy-Squarge inequality? That is a simple question. So replacing the x equal to alpha y, if it is linearly independent, so replacing the given the statement x equal to alpha y. So this is alpha is the real. So mod alpha inner product of mod y and y. So mod alpha means simply inner product of y and y means norm y square. Okay, square root of y and y means inner product of square root of y and y means norm y square. So norm y square equal to that is the value of absolute of y and y. So this value can also be written as alpha y of norm y. Alpha y equals to, what is the meaning of alpha y? This is the scalar multiplication. So this value is replacing by x. So norm x and norm y. So if it is linearly independent, now this is also verified here. Replacing the value of x equal to alpha y. Okay, students. Now, particularly that question is given 10.5.2. If it is linearly independent x and y, it holds. Now, according to the norm condition of the Cauchy-Squarge inequality, absolute of inner product of x and y equal to norm x and norm y. It holds if and only if x and y are linearly dependent. This is also one of the, if it is not given, Cauchy-Squarge inequality is not given in the final examination, this theorem is very important. So that is our assumption, lambda equal to inner product of x and y by inner product of y and y. Same proof. But here, particularly under the norm condition, this is norm y square. So that's why we are taking the value is in the above proof is x plus lambda y. But particularly in this proof is x minus lambda y is taken in Cauchy-Squarge inequality. This theorem is verified. So under the statement is taken necessary part, and we must prove the x and y are linearly independent. This is also one of the independent means if that value is 0 is there. Okay. Already we know the what is the linearly dependence and linearly independent. Okay. Linearly dependent and x equal to alpha y. Already we have to discuss it in the above theorem. That is the converse part under the norm condition. So another one, norm x equal to, by the definition of norm x equal to square root of x and x. These are all propositions, depends upon the Cauchy-Squarge inequality. These propositions are very important, students. Now, especially under the norm condition, norm is also an inner product space. That is the theorem. Norm condition is also an inner product space under the definition of norm x equal to. So, norm x square equal to inner product x and x. Or norm x equal to square root of x and x. Particularly, this value is a positiveness. Positivity is there. Okay. So, first of all, first condition IP, the IP1, IP2, IP3, under these three conditions verified throughout the norm. So, that is also an inner product space. Okay. That is the simple part. Okay. Second one, x and y. We are taking here the condition is x equal to, x and x equal to 0. Norm x equal to 0, x and x equal to 0, x equal to 0. First condition is verified. And throughout the scalar multiplication, norm alpha x can also be written as square root of alpha x and alpha x. So, square root of alpha into alpha bar of x and x. X and x means, so square root of x and x. Square root of mod alpha square means mod alpha. Square root of inner product of x and x means norm x. So, this condition is also verified. Okay. And here x and y belongs to x. Norm x plus y whole square. This is the triangle inequality. Norm x plus y whole square means x plus y and x plus y. This is x and x and y and x plus y and y. Very important concept. Now, according to the this concept, simply easily to qualify, easily to pass the final examination, especially in the functional analysis paper. Now, these inequalities also belongs to operator theory paper. X and x means norm x square. So, norm condition is applicable in this one. So, this is y and x means conjugate of x and y. So, this is z and this is z bar. Z into z bar means two real part of x and y. This value z plus z bar means z plus z bar means 2 into real of z. Z means inner product of x and y. So this is norm x square, this is norm y square. So 2 real of x and y can also be written as 2 mod of inner product of x and y. So apply the and we are taking the Cauchy-Squarge inequality under the norm. This value is norm x and norm y. So enter this value comparing it with a plus b whole square formation. So that's why norm x plus norm y whole square. Finally, triangle inequality is also verified. Norm x plus y less than or equal to norm x plus norm y under this given this proposition. Okay, so in examination, state and prove triangle inequality or prove that norm x plus y less than or equal to norm x plus norm y, means only this is the proof of given this as our assumption. Okay, so under the norm and inner product space, simply that is also norm x square means inner product of x and x, norm x equal to square root of x and x. Through the under the norm representation depends upon the inner product space. Okay. Students, this is the parallelogram law. Listen carefully. One is the, here, this proposition is very most important in the long answer question. Now, these two questions are given, proposition 3, proposition 4, in this 10th unit especially. Okay. Now, these two are given in the long answer question in sometimes. Okay. Just you have to verify in the previous paper. So, 10.5.4, x under inner product over the field of the real numbers. Here the k being the real numbers and the complex numbers. There are two cases under this one. X and y equal to 1 by 4 of x plus y and x plus y, minus of x minus y and x minus y. Now these two identities are verified here. Under the complex numbers of the field elements, inner product of x and y equal to x plus y and x plus y, minus of x minus y, x minus y. Complex numbers means imaginary of the values are also given in this representation, in this identity. Okay, I of x plus iy, minus I of x minus iy, x minus iy. Okay, that is simple assumptions. X and y. First of all, so you have to prove this one. X plus y, find out the RHS value. X plus y value is, this is x minus, this is the x plus y value. This is the, under the first inequality x minus y, that is the B part. Okay, now these two values are, just you have to see this one. Okay, these two values are, this is the first equation, this is the second equation. Now, first equation minus second equation, we have to calculate this one. Okay, so we are getting the value is 4 into inner product of x and y. So, first condition is verified. That is the simple proof. Students, listen carefully. Are you understand here? Please respond. Are you understand?
Yes, sir.
Okay, that is a simple presentation. Next, second one, complex numbers, x plus y and x plus y. So that is the first equation, x minus y and x minus y. That is the second equation. Okay, next one, third one, x plus iy and x plus iy. That is the third equation. Fourth equation is x minus iy and x minus iy. Now, you must find out these four values, What is that? Cycle. Go. Now, x plus y and x plus y means x and x and y, y and x, y and y. Second one, x minus x, x and x, and x and minus y. The minus y and x, minus of minus plus y and y. That is the second, that is the B part. Third part is, C part is x and x, x and iy, iy and x, and plus iy and iy, inner product value. So find out these four values are also find first one, second one, third one, fourth one. These four are, you must calculate these four values in a second identity. Now applying given the symbols, in between the symbols. Now this one subtract this one, and again this value is also, these values are also under addition, and one is the subtraction. Now enter the values are substituting here. We are getting the values 4 of x and y. Okay. Now second identity is also verified. This is one of the most important, students. Listen carefully. Now what is the polarization identity? Okay. Now according to the above proposition, what is the polarization identity? Inner product of x and y equal to 1 by 4 of norm x plus y whole square minus of norm x minus y whole square. If it is the k being the real numbers, k being the complex numbers means now the second identity. So the above proposition is called polarization identity is there. Okay. The above proposition is called, what is that? Now this is according to the proposition. Now we must define under the norm condition. So that is called polarization identity. So your state and proof polarization identity means first of all norm x plus y whole square means inner product of x plus y and x plus y. This is first identity is there. Second one, norm x minus y whole square. This can also be written as norm x minus y whole square. So that is x minus y and x minus y. So this condition can also be stated as under the norm. That is the representation. So these two, real part and complex part, particularly with respect to the inner product space, this representation, these two cases are called polarization identities. In examination, state and proof polarization identity. Okay. Now that is the end of this unit. That is the 10th unit is there. Please note down the 11th unit. Please see the 11th unit, Hilbert space. Students, time is very too less. Please note down the some other important questions. Okay, students. Last 15 minutes is more. Now, successfully. Hello? Sir, any doubts, sir? Okay. Sir, any doubt? Please respond. So, successful.
Important questions tell.
Hello? Chandni, please tell me.
Important questions చెప్పండి sir.
Okay. Okay. From the beginning of successfully 10 units are completed. So overall that 18 units. Now this is very high monotonic part because only 6 in the especially only 8 classes through the online classes, only 8. Now these classes are much more useful. These 8 classes. You please refer in the previous sessions also there through the YouTube, because that is subject point of view. You must refer more than times. Okay. So first 10, according to the first 10 units, easily to get the full marks of main paper. So total main paper, final examination, 70 marks in the final examination. That is the question paper belongs to 70 marks. So 4 essay questions given and 6 you must answer the 5 short answer question is given. So short answer questions we will give the 6 marks. Now essay question is given 10 marks. You must answer 4 essays, 4 into 10, 40 and 5 into 6, 30. So 40 plus 30. So that is the 70 marks paper is there. So according to the 10 units, you maximum, you get awarded the full marks. So full scored paper is there in the first 10 units. And remaining 8 units, I will give some important questions. Define Hilbert space. Please note down. Define Hilbert space. So through the inner product space condition, through the inner product space definition in the first 10th unit, now this condition is also. So an inner product space which is a Banach space. So that is called Hilbert space. Now number of times is given. This example 11.2.1. This example is also given in the final examination more than times. Okay. This is called induced norm. Under the induced norm, this example that is inner product space C of 0 and 1 is also induced norm. So this example is also referred by by the definition of inner product space. Well, for a Hilbert space definition. Okay, second example not necessary here. Okay. Now, for the first example, with respect to the inner product space, now that is the induced norm is applicable in inner product space through the Banach space. When it is the complete of Banach space means complete normal linear space. Under the induced norm of inner product space is called Hilbert space. So that is the simple definition of the students. Listen carefully. Define inner product space means an inner product space which is a Banach space. With respect to the norm induced by the inner product space is called Hilbert space. That is the definition. First of all, inner product space of the induced norm is a Banach space. Now that is called Hilbert space definition. Now all the inner product space example belongs to the Hilbert spaces. So first example of inner product space, second example, third, fourth, sixth example, eighth example. Now these 6 examples are belongs to the inner product space, belongs to the Hilbert space. Okay, define Hilbert space and give the example means those examples are also applicable for Hilbert space. Okay. Okay. See this one. So R cube, R square. Now these are all Euclidean norm. R cube is a Banach space with respect to the Euclidean norm. Means field of the elements are real numbers. Okay. And complex norm means that is the complex unitary norm means complex numbers of the inner product space. That is the complex norm under the norm condition. So that examples are belongs to the fourth example of inner product space, sixth example, eighth example. These 3 examples are also belongs to the Hilbert space for Euclidean norm and complex Hilbert complex norm and for Hilbert space definition. N tuples of the real numbers, n tuples of the complex number. Those examples are in the inner product space. Those examples are also belongs to the Hilbert space. Okay, students, this is the different linear isomorphisms. Define linear isomorphism or simple isomorphism. Now that is the definition. Tx1, Tx2 under 2-dimensionality, that is simply defined inner product x1 and x2 under the 1-dimensional of the part. So x1 and x2 both x1 and x2 are belongs to the capital X. Capital X means that is also first inner product space, second inner product space is capital Y. So in between the mapping is also well defined. So x and y both are in inner product space. Now we must define the with respect to the mapping capital T from x to y is said to be a linear isomorphism. So that is the definition of a bijective part preserves condition Tx1, Tx2 at 2 under the inner product of x1 and x2 at 1. Okay. So that is the linear isomorphism or simply simple isomorphism. This definition is also very important. Now, define completion. Define completion. Now, this theorem is also state and prove completion theorem. This theorem is given in the final examination. State and prove completion theorem by the above definition. Okay. That is also very simple theorem under the Cauchy sequence, induced norm and inner product space. That is the simple understood here. There is no doubt. Okay. Simple direct theorem. This is state and prove completion theorem means this is the direct question in long answer question. Okay. Now this is also a end of this unity. Now this theorem is also given in sometimes as on the short answer question. 11.5.4 give the example of inner product space which is not a Hilbert space. 11.5.3 please note down, that is the simple answer. Give the example of for inner product space which is not a Hilbert space. This is the suitable example. You must mention this this one full. Now give the full marks is here. Okay. Now that question is in sometimes the set of all complex valued functions close interval 0, 1 under their norm is not a Hilbert space. Okay, this example is not a Banach space. The which is not a Banach space of the inner product, that is also called that is not a Hilbert space. 11.5.3 important. 11.5.4 is also important. Okay. 11.5.5. These three are important for short answer questions. Okay. Questions now just you have to observe in this session. Define Hilbert space. Give example and inner product space which is not a Hilbert space. This question is given as on the short answer. Okay. Now prove that the completion. Now above theorem is also given. State and prove completion theorem is also applicable. That is the unique up to an isomorphism. That is the answer. This is the answer. Students, now this one you must present in the final examination. This question is given as on the long answer part, 11.6.2. Okay. Now this is the end of the 11th one. And just you have to see the 12th one, bounded linear transformation on a Hilbert space. This is the 17th unit. This is 17th unit, students. 11th one, 12th one important is given. And some other questions is also given. Please note down. State and prove Riese-Fisher theorem. State and prove Riese, R-I-E-S-Z, Riese-Fisher theorem. Please note down. That is the 13th unit. State and prove Riese-Fisher theorem. Eleventh one, 12th one is completed. Okay, students. Define orthogonal and orthonormal vectors. See this 13th unit. Define orthogonal and orthonormal vectors. State and prove Gram-Smith orthogonalization process. State and prove Gram-Smith orthogonalization process. Now, this proof, you must verify the undergraduation level. That is the linear algebra. Okay. Now that proof is also simple understand purpose. Simple proof of for your understanding purpose. Some problems are also practiced in the undergraduation level. That is the linear algebra paper. See this theorem, state and prove Gram-Smith orthogonalization process. Now that proof is easily to understood here. Find the orthonormal vectors for the given vectors is given. So some other problems are also practiced on Gram-Smith orthogonalization process. Okay, that is the statement of in an inner product space. Okay, and finite dimensional inner product space has an orthogonal and orthonormal basis. That is the statement of Gram-Smith orthogonalization process. 13.3.1. That is the theorem of Gram-Smith GSOP. Simply statement. Gram-Smith orthogonalization process. You must practice the problems depends upon the GSOP. Sir, 7 class lo unnanu pavuguntlo chesta. Okay. This is the 14th unit. State and prove Bessel inequality. State and prove Riese-Fisher theorem. State and prove Bessel inequality. State and prove Riese-Fisher theorem. Now these two theorems are also Bessel inequality. 14.3.1. Without these inequalities, you can't expect the final examination. 14.3.1. This is the Bessel inequality. Simply understood here. There is no doubt. Okay. 14.3.4. This is one of the corollary. Depends upon the Bessel inequality. So state and prove Riese-Fisher theorem. 14.4.1. These theorems are belongs to the operator theory. If you have to choose the 11th paper, now these theorems are also very important in behalf of that paper. State and prove Riese-Fisher theorem. Okay. That is a simple concept. There is no doubt. (14.4.6). Okay, oh, no, that's not necessary. Okay, 14.4.7. This theorem is also number of times is given as on the long answer question. 14.4.7. Now these expressions are equivalent. 1 goes to 2, 2 goes to 3, and 3 implies 1. That is the simple concept. 14.4.7. And if it is not given, 14.4.8. Number of times repeated 14.4.7, 14.4.8. Directly, that is for long answer questions. Okay. Now directly, next you have to see this one, 17th unit. 17th unit.
ఏంది చేతలే
17th unit. Please, students, bounded operators and adjoints. You must see the definitions. S plus T of X means S of X plus T of X, and alpha T of X means alpha of T of X under the operations. ST can also be written as S circle T. Circle means that is the composition of S and T. Okay. Now, according to the condition of norm T, norm T means supremum of mod T of X. This is the mod T of X. Supremum of mod T of X means under the unit norm. So, some theorems are also explained in the previous topics. So, according to the definition, see this one. According to that definition, now these properties, these operators are very important. 17.3.2 definition. Now these are very important in the final examination. 17. Now this is the positive definition, symmetric definition, bounded definition. And according to that, 17.3.4. That is the simple concept. Okay. 17.3.5. Number of times is now this operator number of times is given in the final examination for short answer question. Inner product of T of X and Y means X and adjoint of X and replacing of adjoint means S. S means T star. Star represents the further concept. S equal to T star means that is the further for understanding purpose. Now that is the image of the part is also converting into S of Y. This one is also very important. T of X with respect to Y means X of S of Y. Okay. That can also be written as X of S means T star. Okay. This is the 17.3.6. This is called S equal to T star means adjoint of T. Defined adjoint means this is the definition. Now it read as adjoint operator. T of X and Y equal to X of T star Y. 17.3.6. Okay, students. Now directly, just to add the properties of adjoints. This is very, very important in the final examination. Depends upon the adjoint operator definition. 17.4.1. You must verify the previous papers without the operator, without this question, without the operator. Compulsory operator, their operator for operators properties is given one of the either SI or short answer. 17.4.1. Now these operators applicable depends upon the adjoint definition. S plus T whole star. It read as adjoint of S plus T equal to sum of individual adjoints. And adjoint of lambda T equal to lambda bar into T star. Adjoint of ST equal to T star S star. Adjoint of adjoint T double star equal to adjoint of adjoint equal to T. Norm of adjoint equal to norm T. Norm of T adjoint and T equal to norm T square. Now these properties are simply verified. It is completely based on the definition. Now 17.4.1, 17.4.2. This is also one of the most important. Without, okay, 17.4.4, 17.4.1, 17.4.2, and this one, 17.4.4. This is also very important. Now, these three are very most important in the final examination, students. Okay, that is your understanding purpose. Now, definition of self-adjoint, normal, unitary, 17.5.1. Through the operators, how to define the self-adjoint? Simply that is called Hermitein. T equal to T star is called Hermitein. T into T star equal to T star into T. That is called normal. Okay, sir. Already closed. Unitary is the T into T star equal to T star into T equal to I. Projection of T square equal to T. Okay. Now, this is 17.5.1 is important. And the last but not least, 17.5.2 through the above definition. Okay, students. Because very 17.5.5, 17.5.4, 17.5.5. Only 17th unit much more useful in the final examination. Easily to answerable here. Okay. Okay, students. This 17.5.6 is also just you have to see and verify. Number of times repeated as on the for long answer question. Okay, thank you one and all students, because time is over. Okay, once again wish you all the best and wish you. Hello students.
Yes, sir.
Okay, once again wish you good luck in the final examination. Now this is the very most important session through online classes. Just you have to verify more than times. You must watch through YouTube. Okay. If you have any doubt, please contact us and personally. My WhatsApp number 9989476833. Okay. Thank you one and all. Wish you all the best and wish you good luck.
Okay, sir. Thank you.
Okay.